Welcome to The Explainer. Today, we're going to crack the code on one of the most critical concepts for any aspiring software engineer, code efficiency. So, you've written some code. It runs, it gives you the right answer, but is it any good? This is the question that really separates junior coders from senior engineers. And honestly, it's the key to absolutely acing your technical interviews. To really get why this matters so much, we have to talk about one huge thing: scale. Because in the world of big tech, scale changes absolutely everything. Okay, so just imagine you're working with 1 million items of data. If you use an inefficient algorithm, that could force your system to perform 1 trillion operations. Yeah, 1 trillion. That's a 1 followed by 12 zeros. It is, in simple terms, a total nightmare. And this isn't just some theory we're talking about. For companies like Amazon, Meta, and Google, that kind of inefficiency, it directly impacts the user experience, it makes infrastructure costs go through the roof, and it can literally hurt revenue by millions of dollars. And in an interview, it tells them you're not thinking about how code works in the real world. To really wrap our heads around what efficiency means, let's just step away from the code for a second. Let's think about something a little more familiar, like a library. Okay, so the first method, right? Starting from page 1 and reading every single word. We call that brute force. Sure, it's guaranteed to work eventually, but wow, is it slow? The second method, though, it uses the structure of the data, the fact that it's in alphabetical order, to be massively faster. And this right here, this is the core idea of algorithmic efficiency. So how do engineers and computer scientists actually talk about this huge difference between the brute force way and the smart way? Well, they have a very specific language for it.
They use something called Big O notation. And listen, here's the single most important thing to get about it. It is not about measuring speed in seconds or minutes. It's all about measuring how an algorithm's performance scales.
Now this right here, this cuts through a huge misconception. Big O doesn't care if your computer is a super fast gaming rig or a 10-year-old laptop. It only cares about one thing. How does the number of operations grow as the amount of your data grows? That's it.
So let's see how this actually works. You can think of Big O as a way of classifying algorithms into different levels of efficiency. We call this time complexity.
And this table perfectly illustrates the most common levels you're going to encounter. They range all the way from excellent, like O1 or constant time, down to horrible, which is our ON squared or quadratic time. Yeah, that's the dictionary reading villain from before.
So the really crucial point is to understand the difference in how they scale. A linear time algorithm, O of n, usually involves just a single loop. If you double your data, the work roughly doubles. Simple, right? But a quadratic time algorithm, O of n squared, usually has a nested loop, a loop inside another loop. Now, if you double your data here, the work doesn't just double, it quadruples. It's an explosive growth that just becomes unsustainable fast.
So why have we gone so deep into all this theory? Because this is not just some academic exercise. This is precisely what top tech companies, we're talking Meta, Amazon, Apple, Netflix, and Google, are testing for. They need engineers who can build systems for billions of users. When you submit a solution in an interview, it's being evaluated on these 4 key pillars. And look closely, efficiency, understanding time and space complexity, is just as important as getting the right answer. In fact, it's what separates a good engineer from a great one. This insight is pure gold. It comes directly from a principal engineer at Amazon. You see, they aren't just looking for coding machines, they're hiring collaborative problem solvers who can explain their decisions. Explaining why your solution is efficient is literally part of the test. Okay, let's bring all this home. If you're heading into a technical interview tomorrow, I want you to remember these 3 simple, powerful rules. So remember these takeaways. First, it's all about how your algorithm behaves as data grows, not how fast it is right now. Second, be very suspicious of nested loops. They're the #1 cause of that horrible quadratic complexity. And third, communicate. You have to explain the trade-offs you're making and justify why you picked the algorithm you did. Look, you've taken a massive first step in mastering time complexity. But a truly great engineer also has to manage memory, or what we call space complexity. And often, the most clever solutions involve a trade-off between time and space. And that's a whole new dimension we're going to explore next time. So, are you ready to conquer space?